Finally, let me discuss with a little bit more precision the phenomenon of chaos. In lay terminology, chaos has the connotation of messy, unpredictable, stochastic. But in the context of nonlinear dynamical maps, what chaos means is sensitive dependence on initial conditions. That is, if we start with 2 points which are very close to each other, x0 and x0 plus a delta naught, a small deviation, and apply the nonlinear map n times, do these 2 points run away from each other or do they stay close together? For linear systems, if I would apply a linear map to 2 nearby points, they will still stay nearby at long times. But the crucial feature here is that for nonlinear maps, it is possible that these 2 points will diverge exponentially with a number of iterations. So let's be a little bit more mathematical and write this out. So given 2 points x naught and x naught plus delta 0, where delta 0 is much, much, much less than 1. And the question is the following: what is the deviation after n iterates of the function? So let's call that deviation delta n, and so that's going to be fn of x0 plus delta 0 minus fn of x0. We're only interested in its absolute value, so we want to ask what is the deviation between these 2 nearby points after we've iterated n times. Let's define this difference as delta 0 e to the n lambda. And the crucial point here is that the factor lambda, this is defined to be the Lyapunov exponent, and if it's greater than 0, this defines for us chaos, because it says that these 2 nearby points diverge exponentially in the number of iterations. So let's compute with this definition what the Lyapunov exponent is. So lambda, so I take logarithms of both sides of the equation, I get 1 over n logarithm of absolute value of fn of x0 plus delta 0 minus fn of x0 divided by delta 0. But this, in the limit as delta 0 goes to 0, is nothing more than the definition of the derivative. So this is 1 over n logarithm the absolute value of fn of x0 prime. When we want to take the derivative of the nth iterate, we've seen by the chain rule of calculus that this is nothing more than the product of first derivatives at all points along the orbit of x naught. What I mean by the orbit of x naught is I start with x naught, I iterate to x1, then to x2, all the way up to xn. And so the set of points x0, x1, all the way up to xn, that defines the orbit starting at x naught. And so this is nothing more than 1 over n logarithm of the absolute value of the product from n equals 0 up to n minus 1 of f prime of xi. So the derivative of the nth iterate is just the product of the derivative of the original function at all points along the orbit. In the limit as n goes to infinity, we can write this as, and take the product outside the logarithm, this will be the summation n equals 0 to infinity, logarithm of the absolute value of f prime of xi. So this is defined as the Lyapunov exponent. Notice that if I'm on a periodic orbit, we've seen that all points on a periodic orbit, the magnitude of the first derivative of the function is less than 1. And the derivative is the same for all points along the orbit. So log of f prime is a number which is negative, and I'm adding up a bunch of negative numbers. So on a periodic orbit, lambda is clearly negative. But the amazing thing is that for this very simple one-dimensional map, there are regions in parameter space where the Lyapunov exponent is positive. So if I plot as a function of a, the Lyapunov exponent, then wherever there's stable cycles, the Lyapunov exponent is negative, and it does some kind of behavior like this, but then it crosses over, but then it goes back down again. There's a big minimum at 1 plus the square root of 8, where the 3 cycle occurs, but then beyond that point, it's positive. So these regimes, where the Lyapunov exponent is positive, are known as chaotic regimes. And it is truly amazing that a map as simple as a quadratic function xn plus 1 is equal to axn times 1 minus xn, a simple quadratic function, that the iterates of this function have chaotic behaviors. It's truly an amazing feature of one-dimensional nonlinear maps.